Something happened. I answered the question and I did it correctly, but it didn't click when I clicked the
the
one.
email. Yeah. Yeah. All right, so I think the calculus people are maybe still not here. Don't know how many of them there are, but we'll see. But I want to commend you all on your excellent time management skills. You are the ones who should be the bridge engineers, clearly.
Yes.
All right, there's a quiz. It's not hard today, so just do the quiz. Oh, there's more people. Okay. Well, hello. Hi to the people who are done with the bridge or gave up on the bridge or whatever happened. Hi to the people desperately watching this lecture, trying to catch up 2 days before the exam on December 14th. I'm sure you're there as well. If you're watching on the stream, please do the quiz. I need once you're done with the quiz, so I need 3, 5, 6 volunteers. There can be prizes. Come on down. Say, yeah, come on, yeah. Say it. That is sure, yeah, but the quiz is one question. Yeah. All right, so new people do the quiz. I also need 5 volunteers, I think. Yeah. Come on down. Yeah. Is it? What? The quiz is not open? It says published.
I think it's just not in order.
Oh, no, this is the due date. This is available from. Okay, can you check now, please? Yeah. Okay, cool. Yeah, not for a while. Yeah, come on down. Didn't you say you're coming down? Two more, please. There's Candy. Yeah, don't make me ask Professor James. Yeah, please, yeah. All right. Okay, I'm gonna if you don't like the candy I'm giving you, it's fine. You can choose the candy. So for the red folders, there is red hit taps, and then if you like arrows, that's those ones. And then I didn't have a green candy, but there's this. So please, take a folder, please. You can take your candy as well. The folder is what's important. And please just, mix it up. So just like stand in some kind of order. All right. So let's say that what we want to do is we want to sort those people. And we want to sort it, green and then red. And then like off white, whatever that color is. Okay. So let's do selection sort. How do we do selection sorts? So off white needs to be at the end. You are in the correct place. Okay. Green needs to be next. So that means that we switch places between you and you. Okay. Now you look at those three people. And we're saying, okay, what's the largest one of those? And that might be you, right? So we'll just keep you in place. We just look at those two people. We switch you and you. And oh, sorry, you are off white. Actually, you are your largest. Yeah, go there. Yeah. Okay. Sorry. Let's say we're here. We're here. You're here. You're fine. Out of those four, you're the largest. We switch. Okay. Now out of those three, you're the largest, so you switch. Out of you two, you're the largest, so you switch. Okay. Questions? That's selection sort. Okay. Amazing. Okay. So now that was kind of slow. You could kind of tell that was slow. What would you do if you wanted to sort those guys, fast? Well, you would just say, greens goes there and reds goes here and off white goes here. Right? And that would be it. So that is actually how books are sorted as well, right? So what do? You say, well, like the ones whose code starts with A, we'll pile them on here. The ones whose code start with B, we'll pile them on here. The ones whose code start with Z, we pile all over there. And then we deal with the separate files. So that's kind of the same principle. Thank you very much. You can have your candy. Yeah, thank you. Yeah, so all right. If anyone wants more candy, I'll need to give you like one more sort. So okay, so what I want to do is this kind of sort, and again, kind of to emphasize the point, this time I looked up how many volumes Robert's library has, and it's this much. So in order to sort them using selection sort, which you would need to do, like you would sort them, in order to place them in the correct place on the shelf, you would need 5 million squared iterations over 2, if you remember the calculation, but still 5 million squared is a lot. It's 25 with 12 zeros after that. You would never be done. Okay. But clearly people have managed to do that. So how did they manage to do it? What I alluded to before. So just saying, green goes over there, red goes over there, off white goes over there. Okay, so basically arranging things in piles. So if we're talking about integers specifically, then the piles are going to be especially efficient, right? Because I don't need like a pile of twos. I just need to know how, let me add another one. I just need to know how many twos there are. That's what the pile of twos mean, is like there's two of them. And then there's also two of one. And there's then one of everything else. Okay, so here's the idea. I'll make an array, and initially that's going to be all zeros. And that's going to be the counts. And then this is going to be the count for 0. This is going to be the count for 1, the count for 2, the count for 3, the count for 4, and so on. I will then go through this array, this list, and I'll say, okay, I see a 1. That means that this count will be incremented. I see a 10. That means that the count that corresponds to a 10, somewhere over here, will be incremented. I see a 2, I increment this count. I see a 1, I increment the count over here. I see a 23, I increment the count somewhere here, don't see it. I see a 4, I increment the count here. 500, again, don't see it. And 2, somehow it already became 2, but now it's 2. Okay? Does that make sense? So I go through my list and I update the counts for every number that I see. Once I have that, I just read off the sorted list from the counts. So I say, I don't have any zeros. I have 2 1s. I have 2 2s. Don't have any 3s. I have 1 4 and have 1 10 and so on. Does that make sense? So if I know how many 1s there are, how many 2s there are, how many 4s there are, I can just construct the sorted version of the list. So this is called counting sort. And what this is construct a list of counts where count I is the number of times I appears. And then once you've constructed the list of counts, reconstruct the sorted version of the list using the counts. So it's going to be I times counts I for every I, right? So for example, you have 0 zeros, so this is just going to be nothing, and you have 2 1s, so this is going to be 1 1, you have 2 2s, so this is going to be 2 2, and so on. Does that make sense, kind of in concept? Yeah, questions? Let's write this. So this is counting sort. So we need to create the list of counts. So initially it's going to be 0. And then how long does it need to be? Anyone? How large should the list of counts be so that we have enough to store all the information we need? Yeah. Yeah, +1. Yeah. So yeah, it's sorry, not the length of L, sorry. No. Sorry. Something is the length of L, but not that. Yeah, yes. The max of L. Yes, exactly. Right? So the max of L, why? Well, because we need to be able to store how many 500s there are. Right? So that suggests that we should be able to go to L at 500. So to count at 500. If we need to be able to go to counts at 500, then it should be at least max L plus 1 so that we can go up to 100. Don't need more than that, because if we are able to go to counts at 500, that means that we have all the counts. Make sense? Does this make sense now? So I think it wasn't like easy to come up with, but kind of, yeah. Yeah, so because I want to be able to go to counts at 500. If it's just max of L, then the largest index would be 499. Yeah. Make sense? Okay. So we made that. So now that we made it, it's easy. We just go through every element. And we say counts at E plus equals 1. So that creates this kind of list of counts. Right? Yeah? Question? Yeah.
How do you know that he is going to that element? How do you know that it has size?
Yeah, that's a good question. So how do I know that E is the right element? And the answer is, well, it's got to be because what is E? It's like 1 and then 10 and then 2. And then the way I'm setting it up is counts I is the number of times that I appears. So if you like, we can call it like counts E is the number of times that E appears. Right? So I know because that is what counts E is supposed to be, is how many times did I encounter E. Yeah? Make sense? Okay. So now that we have counts, what we want to do is, sure why it's not aligned. What we want to do is construct the list. So I'll say, okay, result is initially nothing. And then I'm just going through the list of counts. And I'm saying, okay, so I am appending so it's unclear. So this is really I rather than E. We could call it E if we wanted to. There's arguments both ways. So I'm extending res with I times counts I. Right? So this is this idea. So what do I mean by that? Is extend result with no zeros, because there's no zeros in the original list. And then extend results with 2 1s. So 2 times the list 2 so that it's 2 2. And then 2 1s. And then extend with 2 2s. And then extend with 0 3, so with nothing. Extend with 1 4, so with a single 4. And eventually you'd build up the entire list because, you know, you've counted up how many of each element there are. So that's what you need to do. That's what you need to know. Yeah. So let's maybe see how it works, and you'll see in the process. So the answer is I want to make it a list. Oops. Okay, now it's good. So I'll make L be so 1, 10 to 1, 4, 2. I'll ignore the larger ones. And I'll say, sorry, I didn't return res here. So I'll say counting sort L. Invalid syntax. Okay. So the counts is just going to count how many of each there are. That's not that interesting. So counts is now like this, right? So no zeros, 2 1s, 2 2s, no 3s, 1 4, 1 10. And now we're going to go and say, okay, so I is currently 0. Counts I 0, so no zeros. So now there is 2 1s. So I is 1 and counts at I is 2. So 1 times 2, which is the same as I times counts I, is this. And then we're saying extend result with this. So in this case, 2 1s. Make sense? So no 3s. Now I think it's a 4. So this is result now, and I is 3. Oh, there's no 3s. There's 2 as well. So now I is 4, and now we're about to extend with the list 4. So result was this, and now we'll extend it with 4 as well. So now result is this. Make sense? And then we're going to wait around for the 10. Right, so I didn't output anything. And of course, L didn't change. L didn't change because we are returning a new, unlike with selection sort, here we're returning a new result. If we wanted to, it's not easy to make counting sort in place, kind of without creating a new list. You could, of course, if you wanted to, instead of returning res, have said L slice equals to result. What that would do is just copy result over the contents of L. So that's also a possibility. But as it is, we can just say sorted L is counting sort L. And we can look and see that sorted L is the sorted version of L. Make sense? So, okay. So this obviously is just for integers, right? Why is this just for integers? Anyone? Like, what's the assumption here that's crucial? Yeah. Yeah. I set up the counts and I assumed that I can take the element and use it as an index. That only works with integers. In fact, only works with non-negative integers. But that works. You can extend this idea into sorting objects that are not like that. You would have to convert them to integers somehow. We'll deal with that more in 190. Yes.
You mentioned the ESC180, like each letter has the corresponding integer value.
Yeah. Or ASCII. Yeah. We say ASCII. So yeah, that's one way to do it. Now you have more than that, right? So like if you have a word, then you have to have a way to convert the word into an index. And one way is to just say, well, it's going to be like first letter times 10 plus second letter times 100 plus third letter times 1000 and so on. But that would be very large. So what we do is we use something called hashing, which we'll talk more about in 190, which you can use. Now, that comes with no complexity guarantees exactly. So essentially, I'm going to just mention it and not do it right now. But the extension of this would be called bucket sort sometimes. And the idea is put different elements into buckets and sort small buckets. separately. So that's kind of the idea with the different color folders is if there are numbers on the folders, we would say, well, like we know how the folders are ordered, and then for small sets, we can figure something out. So that's the basic idea. But going back to counting sort and analyzing counting sort, how fast is it? And let me just write it out. So assumption counting sort and counting sort. All right. So what's the runtime complexity? Well, we need to look at the different elements separately. So how much does this line take? Well, what we need to do is we need to take 0 and copy it max of L plus 1 times in memory. We need to construct this potentially quite large list. If L contains a very large element, this is very large. Before we do that, we also need to compute max of L. And the way to compute max of L is you've got to go through the entire list. There's no other way, right? So that means that this takes C1 times max of L plus C2 times length of L time for some C1, C2. So what I'm saying is I don't know how much this line takes, but I can say, you know, it's going to be proportional to something like this with some constant C1, C2. What constants? I don't know. Depends on the computer. Why is that? Well, because I need to compute max of L, and that takes some time proportional to length of L. I got to go through the entire list. So here I'm just saying like what's reasonable and what can you not get away with. You definitely cannot get away at not looking at every element of L. So therefore, the runtime is at least proportional to max of L, to length of L, sorry. And we know that that's possible because we have an algorithm for that. And then we need to construct a list of max of L zeros, max of L plus 1. So that takes time. That's at least proportional to max of L. Make sense? So this is the answer. This is how much time it takes. How much time does this take? So we're saying for E and L, counts E plus equals 1. So how much time? Or what is the time proportional to? Yeah. Length of L. Yeah, because it's a simple loop. It takes time that's proportional to length of L because it repeats length of L times. So it would take time that's proportional to length of L. So we can write it as C3 times length of L time for some constant C3. Okay. And finally, this is a little bit tricky. So what are we doing here? We are going through the entire list counts is of size max of L. So at the very least, we're spanning C4 times length 4 time, but we are also, max L, of course, but we are also constructing a list that's of size length of L. How do we construct it? Well, you know, one block of elements at a time. But eventually we will have copied and constructed list of size length of L. So that's going to take us C5 times length of L. And that's because the loop repeats max of L times, but we construct a list of size length of L eventually. So that is kind of tricky, right? Because what we're saying is it's not the case that this loop takes the same amount of time every iteration. If it happens that counts I is very large, then it would take longer because you would need potentially to construct a really, really large list. So what we do is something a little bit clever. We say, well, I don't know how much time every iteration is going to take, except that it's going to be an iteration. So the time is going to be proportional to C4 times max L at the very least. But then I'm saying in all of those lines taken together when run over the run of the entire loop, what they're doing is they're constructing a list of size length of L. So that means that the runtime is going to be also incorporating something like C5 times length of L. Which one of those is larger? Well, I don't know. It could be either, right? Because it could be that the list is just all ones and twos. And the job is to basically construct the list with like 1 million ones and 3 million twos, right? So, and in that case, this doesn't matter. The list just runs with 2 iterations. What really matters is those lines that got executed twice and that take up this much, which is very large in total. Or it could be the other way. It could be that the list is very sparse. It could be that what really takes a long time is to construct a list that's just 2 elements. That's like 1 billion and 5 billion, right? And that's it, like a number 1 billion and number 5 billion. In that case, this guy's going to be larger. I don't know which one it is, but it's proportional to both in some sense, like if one is constant. Does that make sense? So in the final accounting, it's just the sum, right? So it's C1. So I'm collecting the terms for max L. So C1 plus C4 times max of L plus C2 plus C3 plus C5 times length of L. Okay. So we don't care about the constants and big O notation. So the complexity is O of length of L plus max of L. Right. So if length of L is fixed, you can just say the runtime is going to be proportional to max of L because length of L is a constant. If max of L is fixed, so for example, if you know that you have integers that are between 0 and 100 always, you just have a lot of repetitions, then it's O of length of L. If you don't know, you can just write it as this sum. Make sense? So the cool thing is that and a lot of the time, what you have is max of L is fixed. In this case, this is a linear time algorithm. It's just proportional to length of L. Right? Does that make sense? Questions? All right. Okay. All right. So there is a lab on Wednesday where I do want to ask you to do a little bit of recursion. It's going to be a little bit ridiculous because much of the class is not here, I guess we'll just have them watch the recording. So I want to introduce you to recursion, unless, is there questions, anything? Anyone want candy or something? Yeah, we can try. There's this Smarties. I cannot throw that far. Oh, we'll share. Okay, I meant to do it last time. Okay, if anyone doesn't want to pass, let me know as well. Okay, I'm not gonna come in. Okay. Sorry, I have three. Okay, I'm gonna try for you. Yeah. Oh. It was meant for her to get a turn. Sorry, I'll try more. Yes. Okay. Okay. All right, okay, that's what the values are at. So recursion. That's just the question was there is recursion throwing candy, not quite. Although they're both useful skills in life. So recursion just means a function that's calling itself. So I'll start with just the classic example of recursion, which is n factorial. So n factorial, we actually saw that a little bit is equal to 1 times 2 and so on times n. Sorry, quiet down, please. Like, I know that some of you have a sugar high and some of you are disappointed that they don't. So yeah, sorry about that. I'll bring more. So okay, so this is n factorial. So another way to write n factorial is to say, okay, so this is n minus 1 factorial times n. Make sense? So I just rewrote it, yes. It's not about decreasing. This is just like the definition of what it means for what it means to say n factorial. Like one way to say it is this, and this is just another way of saying the same thing. It just like algebraically, right? All right. But this suggests a way of writing the function that's different from before. So I'll say what's factorial of n? Well, it's n times factorial n minus 1. Make sense? And this is just the math of it. Right, so I just defined it that way. So I can now say, okay, all right, there is a problem here, which is what happens if I want to compute factorial of 0? It's going to say it's like -1 times factorial of -1. That doesn't even make sense. And it's never going to stop. It's going to try factorial -2, factorial -3, factorial -4, and so on. So what we also need here is some condition where we stop. So I can say, for example, if n is equal to 0, I'll return 1. And now that's a complete definition of what the factorial is. If it's a positive number, it's just n times factorial n minus 1. If it's 0, it's just 1, so it's not like factorial minus 1, it's not like 0 times factorial minus 1. Which is not correct. All right. So let's see what happens here. So if I say factorial 5, first of all, let's just print it. So that's 120, which is correct. So I'll put a breakpoint here. Go in. So n currently is 5. And now what I'm saying is I'm going to return n times factorial of 4. Make sense? So I know what n is. N is 5. And I can kind of say, well, like, do I know what factorial 4 is? Well, I can look ahead and see that it's going to compute the right number. I can also just trace it to see how it happens that it does compute the right number. Right? So I'll step in. So it's factorial, calling factorial as if it were a helper function. So inside of this call, n is now 4. And it's going to return 4 times factorial 3. So again, I can look ahead and check that 4 times factorial 3 is 24 because factorial 3 is 6. I can also, again, step in and see how factorial 3 is computed. So I go in. So n in this call is 3. I'm busy. So not 0, and that's going to return 3 times factorial 2. So the same with factorial 2. And now we start returning. So one way to think about, so I stopped. So one way to think about how it works is we call this helper function, which happens to be the factorial itself. When n is equal to 4, it waits around for factorial 4 minus 1 to return. And then once that's computed, it returns 4 times factorial 3. Okay. So another way to visualize it is we start with 5. We call 4. I'll usually write just 5 and 4, but the first time I'll write factorial 5, factorial 4. And then factorial 4 is going to call factorial 3. And then that is going to call factorial 2. And that is going to call factorial 1. And that is going to call factorial 0. And now factorial 0 is straightforward. Factorial 0 just returns 1. Right? Because factorial 0 just says, is n equal to 0? Yes, return 1. So factorial 0 returns 1. And that means that factorial 1 returns 1 times factorial 0, which we know returns 1. Yeah.
If you have a negative number, it's always kind of messed up, right?
Yeah, well, also if you have like 1.5 or something, yeah. Yeah. Or a string. Yeah.
So does it print multiple things?
It does. Yeah. Yeah, it's calling itself as if it were a helper function. So that's what it looks like. Okay. So factorial 1 gets 1 from factorial 0, multiplies it by 1, and returns 1. Factorial 2 returns 2, and now we know that factorial 1 returns 1. So that means that factorial 2 is going to return 1 times 2. And that means that factorial 3 is going to return 3 times 1 times 2. So that's going to be 1 times 2 times 3. And by the same logic, factorial 4 is going to return 1 times 2 times 3 times 4. because it's going to say return 4 times factorial 3. And that means that factorial 5 is also going to return the right thing. Yeah. Yeah.
Is this more efficient than just like using a for loop or something?
The question is it more efficient than using a for loop? The answer is no. It's in fact a little bit less efficient. Although in languages that are not Python, this is something called tail recursion, so it would be the same because it would recognize that it's the same as a for loop. We'll get to that later on. It's less efficient. The reason we're doing recursion is that we'll go up to stuff that's easier to write with recursion. This is arguably easier because it's like more intuitive, but the point is not to be more efficient. Although in languages that are not Python, this can be as efficient as a loop. Yeah.
How do you, like, for example, just using the factorial function?
Yeah, sorry. So if you want to look it up now, you can look up tail recursion. Yeah.
Like,
Yeah.
One
I'm printing, you mean this one? Well, because like this is like calling a helper function. Just because you call a helper function, so like you compute like factorial 1. Well, inside that you call factorial 0 that returns 1, doesn't print, it just computes the number. Does that make sense? Okay, quiet down, please. Sorry. Guys, quiet down. Shh. All right, makes sense? So, okay, so what do we need in a recursive function? So we need a recursive step. So that means basically the output in terms of the function itself, but with a simpler input. So in this case, simpler in this particular case just means smaller because like it's easier to compute factorial n minus 1, you're closer to 0, right? We need the base case. And that is for a simple input, the output without a recursive call. And that's it. So why do we need the base case? So one way to think about it is if we didn't have the base case, we would be calling factorial minus 1, factorial minus 2, factorial minus 3, and so on. Make sense? So that kind of suggests that there are 3 rules about writing recursive functions. So one is the recursive step, aka to get the answer, you must know the answer. Right? Because in a way, you need to express the answer in terms of a call to the function itself. And then the second one is need the base case. And that's because why? Because you can't push in a rope. And the third is just f is equal to omega. Okay, all right. It kind of works, doesn't it? So, okay, all right. 6 o'clock, I will see you on Wednesday. Good luck with the bridge. Bye.